All right, let's get started. Lecture 6, finite element interpolation. So a few quick things. I guess we had lab 2 worksheet due on Friday and lab 1 report due on Friday. We'll try to do a quick grade of lab 1 report, and similar to the lab 1 worksheet, I'll have for this lab only. We'll grade, we'll give comments, and then we'll give you an opportunity to correct things and resubmit just for this one, because it's the first lab, so that you get feedback on the types of things that we are going to be taking points off in future labs. So yeah, I'll meet with not Tina, but the other TA is going to be doing the grading for the lab report. And then once we get that going again, probably within this week, so you get a chance to resubmit that one. When lab 2 report is due, you will also be able to do the lab 1 resubmit, only for this lab. So we won't be doing this every other time. A few things also for the lab 2 worksheet, just make sure that you complete the things that are asked for. And there's a few things, units, of course, one is the units, very important. The other one is plotting things on Abacus. Just make sure that you select the correct things. So there's, for example, different measures of stress. And for trusses in particular, we ask for specific measure of stress. The default in Abacus, if you just put stress, it will do the von Mises stress. But that one is not really relevant for the trusses. The one that is relevant is S11, so the axial stress for the trusses. Or for displacements, maybe one of the displacement components is the most relevant, so you should plot that one and not the magnitude, for instance. So just keep that in mind. It's going to be even more important in the future labs when we do the stress analysis or the heat transfer. There's some components, I think, especially for lab 3, for example, there's this notion of stress concentrations. And the stress concentration is different for sigma X and sigma Y. So we ask for specific components of the stress. Then I think for lab 4 or lab 5, there's this beam bending, and then we really ask for normal stresses which are related to bending, shear stresses, because you might get accurate solutions for the normal stresses, but not accurate for the shear stresses. So again, just the point of being careful with what exactly you pick to plot. So just keep an eye on that in the worksheet instructions. We will be very specific about what component of the stress or strain to plot. I think that's it for the lab. Homework 1 due on Friday. So that's what we have due this Friday. Are there any questions about that one that I should address quickly before getting into new topic? No? Are you making progress on homework 1? Yeah, cool. Any other questions? Okay, let's go to the lecture 6, which is finite element interpolation. Just a little bit of where we are, and you will see this diagram also on Wednesday. What is this whole class about? Again, in the first week of the class, we were just deriving this first and second week of the class. We were deriving these discrete equations, right? So this stiffness matrix times the displacement vector equals the forces plus the reactions. We had that, and then we saw some ways of solving that system of equations. That's what you're doing for homework 1. Then last week, we were doing a little bit of math. So this was last week. We were doing this. That one is probably the heaviest sort of math class that we have in this semester, because it's completely new way of looking at a stress analysis problem by actually writing down the PDE and then showing how the standard form of the equilibrium equation, the sum of forces equals 0, or the corresponding PDE, the way you solve it, usually you need to massage that that expression a little bit into this thing that we call the weak form, which has some integrals, right? And then might not make complete sense, but this is what FE solves. And we'll see that when we do this integration part. Today, we are gonna do this approximation of functions. So this week, we're gonna be here. We're gonna do chapter 4 of the book, which is we're gonna learn a little bit about how to interpolate functions. And then next week, I think, we're gonna basically put the two of these together and then then you'll see how the FE actually solves that weak form. So again, what we're gonna do this week is gonna be this, how to approximate functions. And then hopefully next week we can put everything together and actually show how we get the FE solution. A little bit of what the weak form is. This is sort of ahead of time what the solution will look like, and then this is going to be the interpolation. But what we had from last week, this is sort of a reminder of the weak form from last week, was find the function u such that u is in this space of functions, which again, it just refers to some continuity requirement. Such that the essential boundary conditions are satisfied. So these are essential, or also called Dirichlet boundary conditions. And such that that integral equation, which involves the gradient of u, the gradient of w, and then w multiplying b, plus, and these are the natural boundary conditions. So these are natural, or also called Neumann boundary conditions, are part of that equation. And that has to be true for all the w's, which again have to have some continuity requirement. And have to vanish. So W vanishes whenever we have essential boundary condition. So again, the weak form is find the function u, which has some continuity requirement and that satisfies essential boundary conditions, such that that integral equation is satisfied for all w's that also have to have some continuity requirement, and that they should vanish whenever you have essential boundary conditions. That was the weak form. Furthermore, I would just add one more note from what I talked about on Wednesday. A little bit about what do the W represent. And if you remember what I was drawing last class, what I was saying is that the W's allow you to sort of split the domain. Instead of the strong form, which asks for the PDE to be satisfied at every single point, what you can do is you can average the error with different W's. And you basically get as many equations as you pick W's. So this is what I was doing last Wednesday. I was on Zoom, but I was saying, you know, the weak form has to be satisfied for absolutely all W's. And when is the weak form equivalent to the strong form? When you pick infinitely many W's and they're very, very sharp, then you basically are asking for the same thing as the strong form, that the PDE is satisfied for every single point. But the weak form gives you a little bit of flexibility. Instead of saying, I need to satisfy the PDE for every single point, what I'm saying is for every W, I'm gonna calculate the average error associated to that region that the W is picking up. And then I just want the average error for each of these over each of these W's to be 0. That's what the W's are doing. So basically, equation per W such that average error for each region defined by W is 0. That is the intuition behind this weak form, is to define these W's, a few of them. Obviously, the more W's you get, the better the response the better solution you're gonna get. And then we are gonna get one equation for each of these W's, and it's gonna be such that that equation represents the average error over that region defined by the W. So that's what we talked about last week. So finally, what is this finite element interpolation? It's gonna be defining those W's. And it's gonna eventually look something like this. So these are a little bit of looking ahead. But basically, these W's are gonna be defined by a systematic way of defining these n functions. And that's essentially the finite element interpolation. We're gonna find a way of specifying these W functions. Actually, we're gonna call them shape functions or basis functions n. And how can we do that systematically? That's what the point of this lecture is going to be. And these are what the shape functions will look like. These are the most common ones. These are these hat functions. So this one is going to be n1, this is going to be n2, this is going to be n3, and this is going to be n4. And you can already see that I can find a very systematic way of creating these hat functions. Basically, if you tell me I need 4 functions, you just cut your space into 3 chunks, right? And then you're gonna get 2 functions that are complete, and then the last 2 functions, they just have part of the hat. If I tell you give me 5, like split in 5 chunks, then you would split in 5 chunks, and you would just do basically hat functions over all those 5. These are actual functions. They are hats, but they are very, very easy to plot. And then what I'm going to show you is that with these functions, which are called either basis functions or shape functions, with those functions, I can interpolate any function, at least up to a piecewise linear function. How? That's where these UI come in. How? All I need is points here. So if I have this point, this point, this point, and this point, I'm gonna call this U1, U2, U3, and U4. And these are just numbers. These are not functions. These are just so not a function, just a number. Let's say that U1 is I don't know, 2. Let's say that U2 is 2.1. Let's say that this is 1.7. And this is, I don't know, 2.6. So they are definitely not functions, they're just values. And then this function, this sum, U as a sum of the n functions times these values will actually interpolate this. It will give me this piecewise linear interpolation. This is U of H. Actually, I should just say. We'll show in a second how this works. But again, if I just define these hat functions, the only thing that they have to satisfy is they have to be 1. They go between 1 and 0, the hat functions. And they are very easy to draw. Again, if I ask you for 5 chunks, then you would do the same. Actually, let me do that. So let's say that I want the same function. Let's try to replicate my function. So this was the U function, right? So this is U of X. This is the original function that I would like to represent. But I don't know exactly what the form of this function is, but I'm gonna approximate it by using these hat functions. But now instead of 3, let's say that I want to do, I don't know, this many, right? So again, the hat functions will look just like before. I just need to go from 1 to 0. Then this one just has to go to 1, and then has to go to 0, has to go to 1, has to go to 0, has to go to 1. So very, very systematic way. And then the last one ends at 1. Right, where this now this is N1, this is N2, this is N3, this is N4, this is N5, N6, and N7. And for each of those, I'm gonna have a corresponding value. So this is U1, U2, U3. So for every one of these, U4, U5, U6, and U7. And I'll add that these are actual functions of X. The other ones are just numbers. These are actually functions of X. But they are going to be very easy to define because these are just lines, right? So these are going to be something like minus X plus something. And then if I do, I'm just gonna call it UH because it's not my initial U, but it's an approximation. It's gonna be the sum of each of these shape functions times the nodal value. That, if I do that sum, it will give me a piecewise linear approximation. It will just basically, if I am so it's not exactly my function that I want. It's not U of X, but it's close enough. And if I chop into more and more pieces, I get closer and closer to it. And you can see that these n functions, these shape functions that I'm introducing here, follow the same idea of what I was talking about on Wednesday, that at the end, I'll scroll back down, that at the end, what I want to do is I want to be able to systematically define these weight functions in a way that they span sort of small regions of the domain. So you can see that these hat functions will allow me to do both things. They will allow me to, one, interpolate any function u approximately. And then they will also allow me to do the weak form, because every one of these n's is going to allow me to calculate the average error over a portion of the domain. So these are really the secrets of the whole FE formulation. They allow me to do both things. They allow me to interpolate the solution u, and they will also allow me to do these integrals in these chunks of the domain to get the system of equations. Any questions? All right. So now, one thing is that the way I'm doing it above, the way you saw me do it here, I am naming the shape functions corresponding to each node. This, and you can see that this has the same structure as, so these are nodes and these are elements. But here I'm naming the shape functions. You know, if I have 6 elements, I have 7 shape functions. But that's not very modular. When we were doing the truss, we were doing everything for a single truss, and then we were doing the assembly. So similar, we're gonna do it element by element, because similar to truss elements, we want to do operations element by element. And then do the assembly operation that I introduced in the first week. What that means is that I actually do not want to do, you know, N1 and 2 and 3 and 4, because that works. But the problem with that is that then I need to be looking at the entire mesh at once. So that's not very practical. I want to do it in a way that I can just look at every element at a time. So what you can see here is that if I look at a particular element, then for a particular element, all I need to worry about is half of the hat function that goes from 1 to 0, and the other half that goes from 0 to 1. So instead of having 4 or 7 or whatever, however many shape functions, for every element, I just have 2. So the notation usually has this E here, because for every element, I have shape function 1 of the element, shape function 2 of the element. So there might be, you know, 10 of them if you look at the entire mesh, but per element, there's only 2 always, at least for these linear shape functions. So now this looks a little bit more like the idea of the trusses, where for every truss, you have the nodal coordinates of that truss, and now you also have these 2 shape functions. And again, they are just such that they go from 1 to 0, one of them, and the other one goes from 0 to 1. So let's go ahead and define them. So let's say I'm given some random element. Again, let's say that we have X, and then let's say that we have some random element that starts from X1 E of 2 to X2 E of 4, for example. Can you tell me what the N1 function should be and what the N2 function should be? So I'll give you, so I'm not the only one talking, I'll give you maybe 3 minutes to tell me what N1 of X is and N2 of X is. All right, so what is N1 for this element? No, no takers.
Minus half X plus 2.
Minus half X plus 2, I don't know, I will check in a sec. And what is N2 of X? I'll give you a way of doing this that is also very systematic and will work for any X1, X2. Half X minus 1. Let's hope that is correct. So the way I'm going to tell you how to do it is called Lagrange polynomials. It's a recipe to do it. And basically what we want to do is we want this N1 function to be 0 at that point. At point X minus X2, right? So X minus X2. That would guarantee that for sure, if X equals X2, the thing is 0. Now, so this basically guarantees that N1 is 0 at x equals x2. But it doesn't guarantee the 1, right? How do I make sure that it is 1 at x1? All I need to do is scale by the correct factor. So this scaling guarantees that n1 of E is 1 when x equals x1. So in this case, x minus x2 is x minus 4. And then below would be x1 minus x2, so 2 minus 4. So indeed is minus 1/2 x plus 2, correct. But note that this definition that I have up here, that one works for any x1, x2. And we'll use this later on to define quadratic functions, for example. The nice thing about that one is that this is general. And 2, similarly, what I'm gonna do is I'm gonna just say it has to be 0 at x1. So at the top, I'm just gonna put x minus x1e. That guarantees that it's 0 at x1. And then to make sure that it is 1 at x2, I just need to use the correct normalization. It's just x2 minus x1. If I do that, then I'm basically guaranteeing the two things that I want: 0 at a corresponding point, 1 at the other point. So this, for this particular element, is indeed x minus 2 over 4 minus 2. So it is 1/2 of x3. This should be minus 1, yes. So it was correct. But this way of defining it, it's going to be a little bit more general when we do other elements. And using these two functions, I can interpolate basically within the element. It's just any function given two values. Let's just do that. So again, I have x and I have these 2 points. So x1e equals 2, x2e equals 4. I have my n1 function, which looks like this. I have my n2 function, which looks like this. And then now I need two values, and it doesn't matter what they are. I have some u1 value. Let's say, for example, 3. and then some U2E value, let's say 5. So given these two shape functions and these two values, then this function, that function is UH of X is the sum of the shape functions times the nodal values. So that would be the first shape function times the first nodal value plus the second shape function times the second nodal value. If you want to actually expand it, then the first shape function was minus 1/2 x plus 2 times the first value, which was 3, plus the second shape function, which was 1/2 of x minus 1, times the value of u, which was 5. Whatever that gives you, it's going to be the equation of a line, and it's this line. You don't have to expand it. I don't know what this gives you, but whatever, if you expand it and do the sum the fractions, isolate the x and the other number, it will give you this equation of this line. I promise. So again, just to recap, what we have introduced is a way of defining these nice hat functions, shape functions, basis functions inside an element, that we can interpolate any line inside of the element by taking two values and then just summing the first value times the first shape function plus the second value times the second shape function, and that will reconstruct that line. And the nice thing about this is that we found a very generic way of defining those shape functions. We'll do it on code on Friday. Any questions? Yes.
There are attempts to use different shape that linear shape.
What are the? What was the question?
Like for the end function,
yeah,
linear line, right?
Yeah, for this one.
Attempts to make it into different shapes.
Yeah, I don't think I'll do it for this lecture, but the same idea of defining the hat ones you can use to define quadratic ones with the Lagrange polynomials. Actually, let's do that, and then I don't know if I'll get to take the derivative. This was originally for Wednesday, but we can do it now. Can we do better than linear? Yes. Let's do quadratic, and I'll just show you that I'll give you a chance to do it. So for quadratic, a parabola is defined. A line, you only need these two values. You only need the slope and the intersection with the y-axis. So that's why you only need the two node locations to define the n1 and n2. For a parabola, you need one more point. So you cannot define a parabola uniquely with just 2 points. You need 3 points. So a quadratic element will need 3 nodes, just because you need 3 values to define a parabola. So we're going to call this x1e, we're going to call this x2e, and we're going to call this x3e. So 3 nodes needed to define a parabola. And then n1 should be such that it's 1 here, and it's going to be a parabola, and then it should, looks kind of a line. Let me redraw it. But it's a parabola. It's just that that one goes down, something like that. So this is n1 of x. going to be a parabola that is 1 at x1 and is 0 at the other two. N2 is going to be something like this. So N2 is going to be 1 in the middle, and it's going to be 0 in the other two, and then 3. So now we have 3 shape functions, and 3 is going to be something like that. It looks kind of the same color. So this is N3. That one is 0 at the other two, and is 1 at the edge. I'll give you maybe a couple of minutes to try to write what N1, N2, and N3 should look like. What is the equation for N1? I mean, I can give you the values, but it doesn't matter. You can define it for arbitrary, let's say this is 1, this is 2, and this is 3, but it doesn't matter. You should be able to define it for any x1, x2, x3. So I'll give you a couple of minutes to, you can talk to each other. What should this look like? Hint. All right. I don't know if the hint helped, but basically for N1, we need it to be 0 at the middle and at the end. So what we need is, here we need x minus x2e and x minus x3e. If you do that, whatever x2 and x3 are, if you do that, then you guarantee that it will be 0 at those 2 points. And then the only thing that we need to make sure is that it is 1 for x equals x1. So for that, all we need to do is just normalize by the corresponding value. So if you do that, that function is a parabola. You can see that it multiplies 2x terms. So it's gonna, if you expand it, you will end up with some x squared. And the product at the top guarantees that it will be 0 at x2 and x3. And then the bottom thing is just a number, and it's really just to make sure that it's 1 when x equals x1. So for this one, so the second parabola needs to be 0 at the first and at the last point. So here, if I do this, then I guarantee that it will be 0 at the first point. If I do this, then I guarantee that it is 0 at the last point. And then I just need to normalize. So I just need to do this. And if I do that, when I plug in x equals x2, things will cancel out and I will get a 1. And for the last one, again, all I need is, now this one I need to be 0 at the first one. This will guarantee that it's 0 at the first one. I need it to be 0 at the second one. That will guarantee that it's 0 at the second one. And then just normalize so that it is 1 when x equals x3. These are the 3 parabolas. You can plot them. You'll see that they satisfy that. And this works for if you want cubic. Now, if you want cubic, you need 3 terms at the top and just 3 normalizing factors. And they are constructed in the same way. Again, this is called Lagrange polynomials. Now, what is a good degree of elements to use? Honestly, linear or quadratic, because of a couple of reasons. One is, even when you use quadratic, they are flexible enough to have a good interpolation of functions. And the other one is that for Lagrange polynomials, for quadratic, you don't see the effect. But if you add more and more terms, I don't know if do you do any Lagrange polynomials in any of your classes? If you do more and more terms, then you start having a lot of oscillations. So if you have something like a quintic polynomial or something like that, then you get some smooth thing, but you get these huge oscillations near the ends. And so those tend to spoil your solution. So that's why, quadratic is fine, but higher degree is really not used. Cool. Any other questions? All right. In that case, I'll see you on Wednesday. Yes.
So I don't have much time because I have a live, but I need to ask this question.
Yes. Stop recording. One sec.